As we all know, there are many different types of relays used in protective schemes. However, most relays follow the same logic pattern. That is, input, measurement, determination, and output. The input will represent current or voltage or frequency or perhaps other values which exist in the protected circuit at any instant in time. The relay measures these values and then determines if the circuit operating conditions are within normal parameters. Under normal operating conditions, output is zero. That is, a set of open or closed contacts at rest. However, with an intolerable fault level, then the relay output will impose an operating signal on a control circuit, usually in terms of DC volts. This tripping signal is then fed to one or more circuit breakers to cause them to open so as to isolate the faulty circuit. What is the purpose of the circuit breaker? Well, obviously, the relay itself is a small, low-voltage control device, whereas the circuit breaker is an integral part of the high-voltage, high-current power system. In fact, for the protective relay to have any impact at all on the power system, it must be coupled to a switching device. The exception to this is where relays are used to give alarm only. But for action, it must command a switching operation. Conversely, the circuit breaker would have little value other than as a manual switch if it were not coupled to protective relays. The circuit breaker is specifically designed to interrupt fault current, which may be 10 times or more than normal full load current. It achieves this by breaking the current flow in a specially designed interrupter. As the contacts open inside the interrupter, an arc is drawn. It is essential that this arc be extinguished immediately and the contacts thoroughly insulated from each other, so as to prevent a restrike, which could result in considerable damage to the breaker. Various methods are used to quench the arc inside the interrupter, depending upon the size and voltage of the breaker. The quenching medium may be oil, as in the case of this 132 kV oil circuit breaker. In this type of breaker, all three phases are immersed in oil tanks, and the tanks are grounded. This is known as a dead tank breaker. We mention it here because the item does have some significance in protection, as you'll see in later tapes. Incidentally, current transformers are usually located in the bushings here. This type of breaker is usually provided with a single trip coil to operate the opening mechanism on all three phases. In rare incidences, a breaker may fail to open, perhaps due to a problem in the tripping circuit or in the mechanism itself. Indeed, as we shall see, this is one of the conditions that must be protected against. Where breaker operation is critical, an additional parallel tripping coil and circuit is often provided, fed from its own second set of relays. Another type of arc quenching is through air blast, as in this 345 kV breaker. As you can see, each phase has its own interrupter mounted on insulators. As it is insulated from ground, the tank is known as a live tank. Each of the phases is equipped with its own separate tripping coil, and they are usually, but not always, wired in series. Problems can and do occur if perhaps one phase fails to open, or conceivably all three phases open, but not at precisely the same time. This can give rise to severe transients on the system, as we shall see in later tapes. Additional redundant tripping circuits and relays are usually provided with high voltage breakers, that is 230 kilovolts and up. Yet another quenching medium is SF6, sulfur hexafluoride gas. And in lower voltage breakers, arc brake chutes are provided. Vacuum breakers use vacuum as the arc quenching medium. The subject of circuit breaker design is obviously outside the scope of this video program, but further details are provided in other programs. The important factor to remember is that the circuit breaker is capable of interrupting fault currents. There are many other switching devices, particularly in use on the distribution system, such as reclosers, sectionalizers, and oil switches. But in general, these are capable of very limited fault interruption. On the distribution system, fuses are often used in place of the relay circuit breaker combination. The fuse is not so fast or accurate as protective relays, but it does provide satisfactory economical protection for distribution transformers and feeds. Another type of protection frequently encountered at utilization voltage of, say, 480 volts is the direct acting contactor. In one common type, overcurrent causes thermal contacts to open the circuit. In another type, a built-in relay opens the contactor. However, let's return to the thrust of this program, that is, protective relaying of the power system. This circuit shows the elements of a very basic protection scheme. The inputs to the relays are provided by current and voltage. The voltage is measured by a voltage transformer connected to the bus, which may be at, say, 33 kV. The secondary side of the voltage transformer, or potential transformer as they are often called, delivers 120 volts to the relay. This voltage will, of course, rise or fall in proportion to variations in the bus voltage, so it will represent the actual bus voltage to the relay. Similarly, the line current is represented by the input to the relay from the current transformer. We shall be talking more about CTs and VTs later. This circuit breaker is located in the line, that is, the protected circuit. Let's suppose that a high magnitude fault occurs on the line at this point. The relay will detect the intolerably high current and send a tripping signal to open the circuit breaker. Let's look at this tripping circuit. A 125-volt DC system is provided for operation of the breakers. The circuit breaker closing and tripping coils are energized by 125-volt DC from the station battery, as this provides a continuous and reliable power supply. When the circuit breaker is closed, the elementary tripping circuit will look like this. These auxiliary contacts are closed because the breaker is closed, but the tripping coil will not be energized until either 1, the protective relay contacts close, or 2, the manual switching contacts are operated. In practice, there may be other parallel contacts which can open the breaker. Remember, the circuit breaker tripping coil and its auxiliary contacts are normally located at the circuit breaker inside the cabinet. This is probably in the switch yard, some distance away from the relay panel. However, relay operating contacts are located inside the relay. The manual switching contacts are normally located on the control panel. Now, when the relay operates due to sensing intolerable conditions, the relay contacts will close, and this now energizes the breaker tripping coil. This in turn causes the breaker to open and also causes the auxiliary contact to open, so breaking the DC tripping circuit. But it is possible that the relay contacts may bounce open first as the fault is removed by opening the breaker. These delicate contacts inside the relay are not made to interrupt this relatively high current flow through the tripping circuit. So in order to protect the contact surfaces, a seal-in arrangement is usually wired into the relay. It functions like this. When the tripping circuit is energized, the seal-in contactor switch is also energized by the passage of current. This, in turn, closes the seal-in contacts here, and they will remain closed as long as the circuit remains energized. Now, if the relay contacts open first, they will not interrupt the tripping current, as the closed seal-in contacts provide an alternative path. Only when the breaker auxiliary contact opens will the circuit be de-energized and the seal-in contact also opened. When working with protective relays, it is always essential to keep these two circuits separate in the mind. First, the relay itself functions according to the inputs being fed into the relay. Secondly, when the relay does operate, it closes its operating contacts, thus completing an external circuit, that is, the DC tripping circuit of the main breaker. Relays are often tested in place so that the total circuitry can be checked as well. Alternatively, they can be removed from the casing and placed on the test bench for test and calibration. When you remove a relay from its case on the panel, you can see the base contacts. These are providing input from the VTs and CTs or other sources to the relay sensing circuit, and also are providing a continuity of the breaker trip circuit. When the relay is removed, it is always necessary to open the circuits of the incoming VT and to disconnect DC to the relay. Conversely, the CT connections must be shorted. I'm sure you already know why this is so. If the secondary of a CT is open-circuited, when current is flowing in the primary, a very high voltage would arise across the secondary terminals. Of course, the circuit that we have been studying is extremely simple, and we have not specified any particular type of relay. You know that this is going to get far more complicated as we go along. For example, considering the three phases of the same circuit, we now have to include 3 relays, 1 per phase, plus a ground relay, all with their separate CTs and sometimes VTs as well. But before we go on, let's take a short break. Please switch off the tape now and thoroughly review this material in your workbook.